Hello everybody, and welcome back to BioSC 140, Human Physiology. This is the final video for the nervous system lecture, and we're going to cover action potential problems. We're going to use hypothetical cells, and we're going to figure out what their resting member potential is, what the peak of their action potential is, hyperpolarization plays if it takes place, the total excursion of the action potential, the threshold voltage during these hypothetical cells. So there are 7 steps for the action potential problems. You got to start at 1 and work your way all through the 7 steps for the action potential problems. Step 1, determine the sign of the equilibrium potential of the ion. So step 1, determine the sign of the equilibrium potential for the ion. So right here, we look at this. Let's start with the top left example. In this top left example, we have this cell here. We have a CAT ion, cation channel. And as those ions move into the cell, you can see that it's positive. We're going to be adding positive charges to the cell. Since we are adding positive charges to the cell is going to become more positive. So the equilibrium potential for Cat plus is positive. Right here, we can see sign of the ion, positive. Chemical gradient is the ion wants to move into the cell. Positive equilibrium sign. That's Cat right here, Cat plus. So this example, top left example. Concentration gradient wants it to move in, check. Positive ion, check. It moves in, it adds positive charges, equilibrium sign is positive. Let's look at the top right example. We have anion negative. It wants to move into the cell. High concentration outside the cell, low concentration inside the cell. It wants to move into the cell. It wants to add negative charges to the cell. So it's going to make the cell more negative on the inside. So sign of the ion, negative. Chemical gradient goes into the cell. Negative equilibrium potential for that ion. Right here, we have high concentration of cation plus inside the cell. Its chemical gradient wants it to move outside of the cell. So we're removing positive charges from the cell. We're removing positive charges from the cell. It's going to make the cell more negative on the inside because we're removing those positive charges. So sign of the ion, positive. Chemical gradient is out of the cell. It's going to have a negative equilibrium sign. Right here, you can see this bottom right example. Concentration gradient is flowing out of the cell. It's a negatively charged ion, so we're removing negative charges from the inside of the cell. We're making the inside of the cell more positive. So ion sign, negative, chemical gradient is out of the cell. We're removing negative charges. Equilibrium potential is positive. So step 1, check. All right, moving on to step 2. Actually, before we jump on to step 2, let's look at another example. So right here, we have lithium, which is positive. Its concentration gradient is flowing out of the cell. Right here, we have for lithium, its concentration gradient is flowing into the cell, and it's positive. The equilibrium potential for lithium is 110, and the equilibrium potential for lithium is 60. But we don't know the sign. We don't know if it's positive or negative. So let's look at lithium, where the concentration gradient is flowing out of the cell. It's a positively charged ion. We're removing positive charges from the cell, so we're going to make the cell more ... For lithium, concentration gradient wants it to flow into the cell. we're adding positive charges to the cell. So it's going to make the cell more, its equilibrium ion potential sign should be positive. So with lithium, we're removing positive charges, we're making it more negative. So we're going to put a negative in front of that 110. On these problems on the exam, the equilibrium, the value will be given to you, but you'll have to figure out the sign. For lithium, we're adding positive charges, positive. So check for number 1. Let's move on to step number 2. Determine the resting membrane potential. The resting membrane potential, or RMP, is the contribution of ion A plus the contribution of ion B. Well, what's the contribution of ion A? The contribution of ion A is the equilibrium potential of ion A times the permeability at rest. So the equilibrium potential we figured out in part 1, or we figured out the sign, the value was given to us in part 1. So we've got this value now. Permeability will be given to us. So at rest, lithium permeability is 80%, and for lithium permeability is 20%. So what's the contribution of lithium? Well, equilibrium potential of the ion. Equilibrium potential of the ion, so lithium, it's negative 110. So we've got negative 110 times permeability. We have to turn it into a decimal, because it's a percentage, turn it into a decimal, so 0.88. So at rest, the contribution for equilibrium potential contribution of ion A or lithium is going to be the negative 110 times 0.8, or negative 88 millivolts. For lithium, we're in the same process. So its equilibrium potential is 60, positive. We're going to multiply it by a permeability of 0.2, and we come up with 12 millivolts. Now, we add them together. Contribution of A plus contribution of B. We just calculated contribution of A and calculated the contribution of B. So negative 88 plus 12 is negative 76 millivolts. So for this hypothetical cell, the resting membrane potential is negative 76 millivolts. All right, let's move on to the next step, part 3. This is going to look a lot like part 2, but we're figuring out the membrane potential at the peak of the action potential. So last time it was resting, now it's at the peak of the action potential. At the peak of the action potential, it's contribution of ion A plus contribution of ion B. Exactly the same as last time. Just the thing that's going to be different is the permeabilities. The equilibrium potential for each ion is going to be the same. The permeability is what's going to be different. So we've got negative 110 for lithium. We're given a different permeability because it's the peak permeability, 30%. So negative 110 times 0.3, negative 33 millivolts for lithium. For lithium, same process, just we have a different permeability now. So positive 60 times 0.7 is 42. Now, contribution of A plus contribution of B, so negative 33 plus 42, positive 9. So the peak action potential for this hypothetical cell, positive 9. Determine the hyperpolarization. So hyperpolarization is equal to contribution of A plus contribution of B. I think we've seen this before, right? Yeah, so it's the same process. We're just going to have a different permeability value for each. So negative 110, the permeability during hyperpolarization is 90%. So 110 times 0.9 is equal to negative 99. For lithium, its contribution, we have equilibrium potential of 60 times 0.1, so 10% permeability, positive 6 millivolts. Now, contribution of A plus contribution of B. Contribution of A is negative 99, and B is positive 6. So hyperpolarization is negative 93 millivolts. Now, it's a little bit different. We're going to change up what we're looking for. We're looking for total excursion. We're looking for how far, how much does this membrane potential change? So we're going to do absolute value of resting membrane potential plus absolute value of peak action potential. Absolute value of resting membrane potential plus absolute value of peak action potential. How far does it move from resting to peak action potential? So resting membrane potential plus peak action potential, negative 76, we calculated that during part 2, plus 9, we calculated that during part 3, 70, so absolute value of negative 76 plus absolute value of 9, calculated this during part 2 and this during part 3. So we get 76 plus 9 equals 85 millivolts. So the total excursion is 85 millivolts for this hypothetical situation. Moving right on. Determine threshold. Threshold is given as a percentage of total excursion. So there's a few steps that we have to do to get threshold. So threshold is equal to total excursion, what we calculated in number 5, times the percentage of total excursion, which will be given to us, plus or minus the resting membrane potential. Now, we know we actually have to do some planning to figure out if we want to do, and some thinking to figure out if we want to use the positive or the negative sign here. Because in some situations we'll want to add, and some situations we'll want to subtract. The threshold is always going to be in the direction towards depolarizing. Depolarizing means moving towards 0. So we're going to use whatever sign is going to take us towards 0. So let's look and see what that looks like. So given as a percentage of total excursion, so 10% of total excursion. So total excursion, determine that in 5, so total excursion was 85. Times the percentage, so 10% or 0.1. So 85 times 0.1 plus or minus resting membrane potential, or negative 76. Well, we're at resting at 76, we want to go towards 0. So what value is going to be closer to 0? Should we do plus or minus? We want to go from negative 76 towards 0. Negative 76 down here on this graph towards 0. Should we use plus or minus? We're going to use plus. So 8.5 plus negative 76 is going to give us 67.5 millivolts. That's this blue hashed line. We're going to be at negative 76 down here at resting. We want to move towards 0. It doesn't make logical sense if we go away from 0 for an active potential. We want to go towards 0. Negative 67.5 millivolts is the threshold voltage. So let's put it all together. We can even put this on a graph, just like we saw throughout this lecture. Just this is for a hypothetical cell. In this lecture, we saw it for a human cell. Resting membrane potential, negative 76 millivolts. Threshold, we're depolarizing, we're going towards 0. So threshold is negative 67.5. We get to our peak at positive 9 millivolts. We then repolarize past resting membrane potential to a hyperpolarized state, negative 93. And then we get back to resting membrane potential. All right, if you have any questions on these problems, please let me know. There are a few more examples for you to try posted on the page, and there will also be more practice problems in the group problems. Once again, I'm here to help. If you have any questions at all, please email me, let me know. Take care.